Hi everyone, and welcome to our lecture video. We are going to finish up Unit 3.1 in our videos today and also have some other videos about Unit 3.3. In our last class, we started talking about intermolecular forces and introduced ion-ion forces, which is another way of talking about ionic bonding. We talked about ion-dipole forces, and we briefly introduced dipole-dipole forces, which we will review for a moment today, but really just in the hopes of talking about hydrogen bonding, which is a special type of dipole-dipole force. So as a reminder, a dipole is another way of saying a polar molecule. So we have a partial positive end, and we have a partial negative end, as indicated by the lambda plus for partial positive and the lambda minus for the partial negative. And we said that dipole-dipole forces are a type of intermolecular force when a dipole or a polar molecule is attracted to another dipole or another polar molecule. We talked about CH3Cl in our last class, and we drew the intermolecular forces as a reminder using these dotted lines or dashed lines to indicate that these are the intermolecular forces that we're looking at. So we also alluded and said that there has to be a special type of dipole-dipole force because we know that the more electronegatively different, the more polar the molecule is. So if we're talking about covalent compounds, meaning molecules that only have nonmetals, the biggest difference in electronegativity can come from hydrogen, which is our weakest, least electronegative nonmetal, and our most electronegative nonmetals, which are nitrogen, oxygen, and fluorine. So this is a special type of dipole-dipole force that we call hydrogen bonding. And this specifically happens when hydrogen is bound, aka bonded, to a highly electronegative atom like nitrogen, oxygen, or fluorine. So when we see molecules that contain H bonded to N, O, or F, that means not only do they have dipole-dipole forces because in fact they are polar, but they also have hydrogen bonding. So let's look at ammonia and water. I know that ammonia, the N is going to be in the middle. So we have N, and we have 3 hydrogens around here. And we also have a lone pair on this nitrogen. Now, if I wanted to ask you where the partial negative and the partial positive was, hopefully you're able to say that the partial negative is going to be the end where the nitrogen is, and the partial positive is going to be the end where these hydrogens are. Again, the reason that this is partially negative is not because there's a lone pair right there. It's because the nitrogen is more electronegative, significantly more electronegative than the hydrogen. So it's pulling on the electrons in the shared covalent bonds to make that more partially negative. Now, if we had an ammonia molecule next to a water molecule, the water molecule would want to arrange itself so the partial positive end is closest to the partial negative end of the ammonia. So if I wanted to draw this in, we could draw it like this. I know the hydrogen end of water is going to be more partially positive because we have a lot of experience looking at the polarity of water already in our class. So we're able to say that this partially positive end here and this partially negative end here, we would be able to say that there's going to be an intermolecular force between the nitrogen of the ammonia and the hydrogen of the water. So because this is a nitrogen and it's attracted to a hydrogen here, we would say that this is hydrogen bonding. Now, a couple of things to note. Each of these molecules have to contain a hydrogen-nitrogen bond, a hydrogen-oxygen bond, or a hydrogen-fluorine bond. Those things have to be true to have hydrogen bonding. If we see hydrogen bonded to any other not nonpolar, any hydrogen bonded to a nonmetal, that doesn't automatically mean hydrogen bonding is happening. But specifically, we would say that this is an H bond or hydrogen bond. Now, what's confusing to students sometimes is we call this a hydrogen bond, but this is still a type of intermolecular force. So it's not exactly bonding like how we spent all of Unit 2 talking about, but we call it a hydrogen bond specifically because this type of dipole-dipole force is so strong, it has the same strength of attraction like other bonds do. So hydrogen bonding is still a type of intermolecular force, but it's just so strong that we call it a bond. And it's really important to understand hydrogen bonding because gives us all of the kind of physical and chemical properties of water that we're going to spend the next couple of units exploring a lot more. We notice that if I have one water molecule, like how I just drew on the previous, if I wanted to draw the individual bond dipoles, right? We know that we would have an individual bond dipole this way and an individual bond dipole this way, which means that we technically have a partial positive on this hydrogen, a partial positive on this hydrogen as well, which means we have two partial negative opportunities here on the oxygen. So that means one water molecule is able to participate in up to 4 hydrogen bonds. So we notice this central water molecule, this one partial negative can be attracted to the partial positive of another water. We also can have hydrogen bonding with another plus over here, and so on and so on and so on. So water is able to participate in up to 4 hydrogen bondings per water molecule. And if we look at that over a larger span, we're able to see that here we start to get what looks like some sort of structure of how water, specifically in this case, liquid water, looks. It doesn't necessarily have a true lattice structure, how we think about ionic solids having a lattice structure, but over a really large span, you might start to notice that there is a little bit of a pattern to how this looks. And this is what ultimately gives a lot of unique properties of water, like its high boiling point, which is good because we live on Earth that has a moderate temperature, which is why water is able to exist in the liquid form. Also, hydrogen bonding is really important is because hydrogen bonding keeps DNA strands paired together. When we have our different base pairings, specifically here, this oxygen is hydrogen bonded over here. This hydrogen bonding occurs with this nitrogen, and so on and so on. So between guanine and cytosine, we have 3 hydrogen bonding opportunities. And between adenine and thymine, we have 2 hydrogen bonding opportunities as well. So in our DNA, it's held together by hydrogen bonds, which is really good because hydrogen bondings are one of the strongest types of intermolecular forces, which means it's really hard to pull DNA apart from each other, which is good because we want our DNA to stay together unless it's undergoing replication and other biological processes as well. So that was our video all about hydrogen bonding. Our next video is going to be all about what happens with non-polar molecules because they can still participate in some intermolecular forces. See you then. Hello, and welcome back to our video. We are going to be talking all about intermolecular forces that involve non-polar molecules. And before jumping into our final 2 types of intermolecular forces, we have to introduce a new concept called polarizability. So if I break up this word, like we've done for a lot of words in chemistry, polar means to separate charges, and ability means ability. So the polarizability of a molecule is the ability to make something that was not polar. The ability of how can I make something that has an even distribution of charge actually slightly polar. And the reason that is because polarizability is the extent to which the electron distribution in an atom or molecule can be distorted by an external field. Distorted means an atom or a molecule that's normally nonpolar, how can it be distorted by something else, an external field, meaning either another polar molecule or even another nonpolar molecule? How can we distort it to have somewhat of a partial positive and somewhat of a partial negative? And when we think about polarizability, we're going to be thinking about atoms and generally like spherical atoms, which I know isn't necessarily true, but just go with me here. So if I have some spherical atom, right? And I have some sort of nucleus in the center. I know that my electrons live outside of the nucleus. We spend a lot of time talking about, okay, they live in different orbitals, and all of those orbitals have different shapes. But for generalization here, I know that electrons live outside of the nucleus. So we have some electrons here, we have some electrons here, we have some electrons here, and some electrons here, right? So we know also that electrons are never motionless. They always have motion. They're always moving. I don't know necessarily where or how quickly they're moving at a given time, but I know that they're moving. So these electrons are constantly moving around space, right? Again, this is a generalization, but go with me here. If these are all moving equally because they don't want to be by each other, this would be nonpolar, right? Because it's an even distribution of negative charges around our around our positive nucleus, so everything is balanced out. So a general atom wouldn't necessarily be polar by itself. But what we're going to explore is what happens if my electrons just happen to be on one side of an atom at the same time. Meaning, what happens if we have, what happens if we have an electron here at a given time, an electron here at a given time, an electron here at a given time? In that instant, we're going to say that we actually have a partial negative here, and in an instant, we have a partial positive here. This can either happen naturally or it can be induced by something polar nearby. So the ability for something to become polar can be characterized or increases with the greater number of electrons, meaning the larger the atom or the larger the molecule, the more polarizable it is. Because if we have a greater number of electrons, that means that there's a greater likelihood that we can form some sort of quick polar molecule. So we have a greater chance of forming a polar substance in an instant. This also means that there's a more diffused electron cloud. As we get further and further and further away from the nucleus, it gets more and more and more diffused, which kind of goes with our bullet point number one, meaning that if there's more and more space to occupy, the electrons are going to diffuse further and further and further out, thus then potentially creating a partial positive and a partial negative. So the next part of, or the next intermolecular force, our second to last, is a dipole-induced dipole. Again, a dipole is a polar molecule, but now we have this term induced dipole. If we think of the word induced, maybe you know someone who has delivered a baby before, and they have an induced labor. That means that they're being forced to undergo labor to deliver a baby or deliver a child. So an induced dipole is when we induce or force something that normally is nonpolar into becoming a polar molecule, which means these are the intermolecular forces between a polar molecule and a nonpolar molecule. In our language, induced dipole means a nonpolar molecule. So like we just said, right, on the previous slide, we said that if I have some atom and there's electrons that are evenly distributed within the electron cloud, there's no dipole. It's not polar. There's no sort of polarity to this specific atom. But let's say I bring in a polar molecule to hang out next to what was my nonpolar molecule. This guy right here is now transformed into this. So let's think about it a little bit more. The electrons that were in this atom are now, if it comes down here, and I have a friend nearby, let's say that this is water. This is an oxygen. Oop. This is an oxygen. This is a hydrogen. This is a hydrogen. I know that the oxygen in water is more partially negative. And if that partial negative is hanging next to what was a nonpolar molecule, or nonpolar atom, the electrons in that atom are like, I'd rather not be close to a partial negative because we know opposite charges repel each other. So as a result, the electrons that were hanging out here evenly distributed, let's say there were 3 electrons hanging out or 4 electrons hanging out evenly in this atom, those 4 electrons would want to move away from the polar molecule, specifically the partial negative end, right? And if I have electrons that are moving further away to one side of the atom, we have now induced or forced a dipole to occur. So as the molecule with the dipole, we say that this has specifically a permanent dipole, meaning water is always polar. As something with a permanent dipole approaches something that is normally non-polar, we can induce a dipole or force polarity onto something that wasn't normally polar because the electrons in the electron cloud of the non-polar molecule do not want to hang out nearby to the partial negative. If the partial positive end was nearby, the electrons would want to hang out near the partial positive, and we would see the opposite effect occur. So in this case, these are the intermolecular forces between a non-polar molecule and a polar molecule, and we could draw a dashed line between these guys to indicate that we have a dipole-induced dipole. So the last type of intermolecular forces are called London dispersion forces, or van der Waals forces. Sometimes you'll see that. Van der Waals forces. Both of these, totally fine. I tend to call them London dispersion forces, and most people generally do. I also abbreviate these as LDF a lot of the time too, because London dispersion forces is a long phrase. So the final type of intermolecular force that we're going to explore are what are the intermolecular forces between two or more non-polar molecules. We know that non-polar molecules are just that, they're not polar. However, there's some sort of very weak intermolecular force that holds these substances together, and that is because we form what is called an instantaneous dipole. On the previous slide, we just said that water has a permanent dipole, meaning that water will always be a polar molecule because of the electronegativity difference between oxygen and hydrogen and the asymmetry in the molecule as well. But what happens here is that when we have nonpolar molecules, we can form an instantaneous dipole, which is just that, a dipole that occurs in an instant. So it's there for an instant and then it's gone. But we're going to see how that ripple effect can ultimately create some intermolecular forces. Okay, so in this video here, and we're going to keep playing this animation, we have two neon atoms. Neon atoms by themselves are nonpolar, right? Because we have our positive nucleus, the electrons are distributed throughout, but I do know that electrons are constantly moving. So in this animation here, we see that we have electrons constantly moving. And we notice that in an instant, at one given time, we have all of these electrons in this neon situating itself on one side. And because of that, electrons arrange themselves close to each other for an instant. Again, this is only an instant because electrons don't want to be near each other, but for an instant, they happen to be near each other because they're constantly moving. As a result, this instantaneously creates a partially negative side of what is a nonpolar atom or molecule, but that also means I create a partial positive side. And as a result, if these neon molecules or neon atoms are really, really close together, that's going to force another instantaneous dipole on another side too. So let's pause right here. We're seeing that in this instant, on this end, we're able to say that on the left neon atom, we have all of our electrons situated on the left side. So we create a negative charge, which means the other side that's lacking electrons creates a instantaneous partial positive, right? And if I have a neon next door, the electrons in that neon are going to be attracted for that instant to a partially positive. And if I have hundreds and hundreds of thousands, we start to see a ripple effect. We start to say that, okay, over time, these electrons are starting to move and ripple through to create a partial positive in one side, then they move away, then a partial positive in the next one, and then move away. So this instantaneously creates a partially negative side and repel electrons from an adjacent atom, and that creates another instantaneous dipole. And then that would repel electrons from another adjacent atom, creating another instantaneous dipole. So while these are very, very, very weak, this is how nonpolar substances stay together, because these intermolecular forces, albeit they're weak, ultimately help hold these different interactions and different forces together. So one big thing is that since all molecules have electrons, all molecules will always have London dispersion forces. Any single substance will always have London dispersion forces, regardless of polarity. However, nonpolar molecules, this is the only force that it would have. If we have water, it would have hydrogen bonding. It would also have dipole forces, but it would also have London dispersion forces because water still has electrons. So we can form even stronger instantaneous dipoles as well. So we're going to leave off on this concept check. So take a moment, identify the molecule that is capable of forming stronger intermolecular forces, and identify the forces that are present. Okay, so the first thing we get to ask ourselves is N2 and H2O polar or nonpolar? So N2 we see here is nonpolar because those are equal electronegativity. So this is as nonpolar as we can get. And we know from our extensive experience that H2O is polar. So because N2 is nonpolar, the strongest intermolecular force it could exhibit is London dispersion forces, meaning if I have a vessel of nitrogen gas, the gases are held together by London dispersion forces. Water, however, has London dispersion forces, we know, because all substances always have London dispersion forces. Because it's polar, it also has dipole-dipole forces. But because we have hydrogen bonds, meaning H bonded to oxygen, we also have hydrogen bonding here. So water has these three types of intermolecular forces, while N2 only has these. So to wrap up our unit 3.1, and we're going to do some practice problems at the start of next class. The strongest intermolecular forces to weakest are ranked here, and it's in order of how we talked through them. We have ion-ion forces, ion-dipole forces, hydrogen bonding, then dipole-dipole force. We didn't talk all too much about ion-induced dipole because we don't really see them, but it's the same fundamental principle of dipole-induced dipole, except instead of a polar molecule, we have an ion present. And we have then dipole-dipole forces and then London dispersion forces. So with that, we are going to wrap up here. And we have one more video, and I will see you all in the next class. Bye, everyone.